Welcome to lesson number 6. Today we're going to be looking at graphing primary trig functions. And we're going to be looking at what a periodic function is. So a periodic function is a function whose graph repeats regularly over some interval of the domain. And so in these examples, my domain runs from 0 to 16, and you can see there's a repeated interval of my function. And so the length of the interval that's repeated is called the period. And then we have, and so let's look at the period first of all. So period, if you've taken physics, we know that is equal to t. And the period, the point that's repeated, is going to start at 0, and then we move up this graph, we move back down, and then we move back up. And this is where we have that repeated motion. So if I look from here to here, it's going to be the same here to here. And that period is equal to 8 units. Now we have the amplitude of a periodic function, and this is defined as half the distance between the maximum point and the minimum point of the function. And so the amplitude, it's easier to see when our graph is, it's symmetrical at the halfway point, but graphs aren't always like that, and that's what we see in example B here. But the amplitude, if it's the halfway point or half the distance between the maximum and minimum values, here's my maximum value at positive 10, and my minimum value here is at negative 10, and it's a halfway point, so we would divide that by 2. This would be 20 divided by 2, or 10 units. Now we can even just look at that by looking at our graph. So if this is half, then from 10 to 0, that's 10 units, and from negative 10 to 0, also 10 units. Now let's look at example B, where we want to determine the period and amplitude for this graph, this periodic function as well. So the point where this motion is repeated, so I'm starting here at negative 1, and I go up, go back down, and this is my repeated motion. Oh, sorry, that's not my repeated motion. This is my repeated motion. So I go up, I go back down, I go up, I go back down. So right here at 5 is my repeated motion. However, I didn't start at 0, so sometimes we would look at this and say, whoa, it looks like the period is 5. However, I started at negative 1. So if I were to take this graph and shift it over, starting at 0, then my period would be 6 units. And so remember, we're measuring the length. So from this point to this point, negative 1 to positive 5 is 6 units in length. The amplitude for this function is again the maximum point, which is positive 6. And then we want to subtract my minimum point, which is negative 2. And we want to divide this by 2. So 6 subtract negative 2 is going to be 8 divided by 2 is 4 units. Now in example C here, we can start counting the period anywhere along the graph. But because I'm at 0 here, and if I look at where the repeated motion is at this point, we can just count from here to here. And that looks like 10 units. So my period, which is equal to t, is equal to 10 units in length. Now the amplitude for this graph, remember, is the halfway point between the maximum and minimum value. So my maximum value is 6. My minimum value is positive 2 divided by 2. We would have 4 divided by 2, or 2 units in length is my amplitude. Now when we're graphing these primary trig functions, we're going to learn about the graphs sine x, cosine x, and tan x. And to investigate these functions, we're going to be looking at these angles for a domain between 0 and between 0 and 360 degrees. And then we're going to be looking at graphing those according to their radians. In this next exploration, we're going to be graphing y is equal to sine x, where x is in degrees. And before we do that, we're going to complete this table of values for for x is equal to 0 to 360 degrees. And we want to give our answers to 2 decimal places where necessary. And so what we're going to be doing is for each of these values, we're going to, these angle measurements, this is my x value, and when I plug them into the function sine x, that's going to output my y value. So if I plug 0 into sine x, this is going to be equal to 0 for the ratio. And so what we need to make sure is make sure your calculator is in degrees, because we're doing this question, which is in degrees. So you go to mode and shift over to degrees, clear. And now what I'm going to do is I'm going to type in things like sine 0. And you get 0. And then sine 30, you should get 0.5. Sine 60, you should get 0.866, but we want to round to the nearest 2 decimals. So sine 60, 0.866, but we want to round to the nearest 2 decimals, so 0.87. Sine 90, it's also going to be 0.5. And we would just, 1, not 0.5. And then we would just continue with this trend, and it's going to go down to 0.87 again. And we want to put all these values into the table. So this is what your table should look like. Now that our table is complete, we want to plot the points on our grid below, and we do not want to join the points yet. So I'm going to actually, let's zoom in a little bit here. So we are graphing the points that we just found in our table. So my first point is going to be at 0 degrees and 0, and so we're going to be right here at the origin. My next point is going to be at 30 degrees and 0.5, and this graph goes up by 30 degrees. So 30 degrees and 0.5 is going to be right here. And then 60 degrees and 0.87. So this goes up by 0.2, so 0.2, 0.4, 0.6, 0.8, 0.9 would be here. So 0.87 is about there, and then 90 degrees and 1 will be here. And then our graph starts going back down. 180 and 0 degrees. And then we start dipping below into our negative quadrant. And so at negative 210 degrees, we're at negative 0.5. 240 degrees, negative 0.87. And then 270 degrees, we're at negative 1. And then we go back up. So this is what your graph is starting to look like. Now we want to look at those points, and we're going to now do we're going to graph y sine x. So if I type in sine x, my graphing calculator, and press graph, I'm going to get something that looks like this. However, this is not the correct window settings that I'm using, so we want to adjust the window settings that were given in this question. So my x min is going to be negative 360. My x max is going to be 540. I have a scale of 30 degrees, and then I'm going to have a y min of negative 1.2, 1.2, and then a scale of 1.2, and then we'll graph. And this is what our graph begins to look like. So on the grid, we want to copy this graph onto our graph over here. And just notice that it's a periodic function, so another thing we can do is kind of just mirror what we see on this side over here. Now this is what our graph is going to look like after copying, and we're extending from positive 540 to negative 360, and actually I should include these points over here as well. And this is what our graph now looks like. And we can also join these points now. And so here we see, as we join our points, our periodic motion and the intervals that are being repeated, like so. Now, the graph shown in B is just the partial graph, and this is showing a restricted domain, so between negative 360 and 540 degrees. And now what we want to do is we want to state the domain and range for the graph we just completed. So the domain, this is a where x is defined on the set of real numbers, so where there are no restrictions for my x value, we would say that the domain is x is an element of real numbers such that r is an integer. And so, and not an imaginary number, an integer, r is equal to I. So our any angle really is going to work on this graph, and we will get an output of a y value for that. The range, however, y has to be greater than or equal to -1, but less than or equal to +1 on the graph we just completed. The amplitude, if we go from the max to the min and divide by 2, would be equal to 1. The period of our graph, if we look at the period where there's repeated motion, so from 0 degrees, I go all the way down back up to 360 degrees, we could say that the period, or this rotation, is completed every 360 degrees. And then the x-intercept of our graph, well, our x-intercept is going to start at 0 degrees if we start positive, and then we essentially move every 180 degrees. And formulaically, we could describe this as the x-intercept is equal to 180 n. And the y-intercept, the point that it crosses my y-axis, is at 0. Now, if we were to express this graph in radian mode, we want to write down the graphing calculator window that the student should use. So in radian mode, first of all, if we look at the window settings for the graphing calculator that we did use, you'll find that in the previous example at option C and in the exploration, but it was -360, 540, and 30. So all we need to do is change that to radian mode. And the y value, however, is still the same because that was the actual value of the ratio, which remains the same. So for my y window settings, we could keep it as -1.2, 1.2, and 0.2. However, for my radians, 360 degrees would be -2 pi. 540 degrees, so if we think about 360, remember that 360 plus 180 is equal to 540 degrees. Now, in order to convert this into radians, we can use our conversion, or we can just say, well, a full pi would be 2 pi, a full rotation is equal to 2 pi, plus a half rotation would be equal to 3 pi. And so 3 pi is is equal to 540 degrees, and the every pi over 6 is the scale of our x values. And then we want to sketch the graph of y is equal to sine x for x is between 0 and 2 pi. Well, that's just between 0 and 360 degrees, so just a rough sketch of what this would look like is like so. This is 0, and then we'll make this 2 pi, and at 180 degrees we'll make that pi, and so it'll look something like this, where this here is pi over 2, and then this here would be 3 pi over 2.